Hello, and thank you for joining this instructional demo on optimizing drainage design workflows. I'm Jessica Jeffries, a product manager at Innovise, an Autodesk company. I've been working in drainage design for over 15 years, helping engineers, designers, regulatory authorities, and water utilities get the most out of their drainage design software, and have become passionate about finding ways to increase the uptake of green infrastructure elements in design. To start, let's look at the learning objectives for today's session. We'll be looking at the workflows from Civil 3D to InfoDrainage and back using the InfoDrainage for Civil 3D tool. We'll be covering all aspects of the drainage, all of the elements from traditional pipes and manholes through to green infrastructure elements. Depending where you are in the world, these green infrastructure or sustainable drainage elements might be referred to as something else: SUDs, WSUD, LID, BMPs, or stormwater controls. It's a bit like acronym bingo with these more sustainable approaches to drainage. But we'll be looking at those in that exchange of data as well. We'll also review some pointers on round tripping data, as it's often required to adopt multiple iterations throughout the design process, and we want to help reduce the risk of errors being introduced there. First, I'll give you a brief introduction to Innovise and discuss why these learning objectives are important to optimizing drainage design workflows. Innovise, an Autodesk company, is a global leader in building innovative, industry-leading software for the water industry for over 35 years, serving thousands of clients, including the largest utilities, design firms, consultancies, local authorities, and refining plants around the world. Innovise focuses on software solutions across the water sector, enhanced with artificial intelligence and machine learning. So from modeling and analysis to support your planning, to projects planning for storm, sewer and flood, to asset management to support the operations and maintenance of your infrastructure assets, to analytics to support your challenges for drainage design and analysis, we're here to support you. Today, we'll be focusing on drainage design and analysis. And to start, let's look at some of the specific drainage design challenges that we can help solve. Here's some of the challenges that we hear around drainage design. Planning permission or consent for any land development is dependent on a sound drainage strategy, but we've heard that increasingly constraints and project costs mean that although it's important to get this right first time round, it doesn't always happen. Delays to that approval can then affect the construction timeline or can impact consultant engineers' margins as well as their customers. And many of these drainage design challenges that we hear are linked to the exchange of data with other packages or adopting iterations. So with our InfoDrainage product, we've built an integration with Civil 3D that installs as a ribbon to allow data to be exchanged via parts mapping. First, a brief look at InfoDrainage. Ensuring that you can accurately represent and analyze traditional and sustainable drainage is fundamental to InfoDrainage. We've seen plenty of design packages that support part of the drainage design or rely on complex modeling techniques to try and represent green infrastructure elements, which can result in the graphical representation not actually matching up with the design, the drawing, and lots of rework in CAD packages each time the overall site design is updated. InfoDrainage can offer accurate graphical representation, but also hydraulic representation, ensuring that the water passes through these green infrastructure systems central to the hydraulic engine, as well as giving consideration for those different levels of filter media, exactly how much there is, the porosity, and the effects those structures have on slowing down the flow. So we can see in detail in this visual long section here that the performance of all the structures can be seen in detail, the different levels, and all of those different structures across the site and how they impact on each other can be reviewed. This helps us have a better understanding of how the design is performing, and with additional graphical feedback on the plan, such as pipe capacity being exceeded or flood risk level warnings, we can help to inform the user the specific areas that may need further optimization. So moving on and focusing in on the challenges that relate to BIM compliance and the data exchange with Civil 3D. Why is this such an important part? Well, as we've noted from the overall challenges, the drainage design rarely happens in isolation. We need to use data from a range of data sources, and we don't want to duplicate effort when we're doing that. So designs often need to be taken from concept through to effectively an as-built construction level, and will involve iterative changes throughout the process, which can be painful and time consuming. With the seamless data exchange with Civil 3D that includes a representation of all aspects of the drainage design, we can optimize that workflow so that engineers can efficiently represent their design, giving greater confidence in the validity and accuracy of the design information. Moving on specifically to info drainage for Civil 3D. Info drainage that you've seen is a standalone drainage design package that can be used without Civil 3D, but with info drainage for Civil 3D as well, we can make maximum use of the existing work already done in Civil 3D and ensure our overall site design remains up to date. Info drainage and info drainage for Civil 3D are separate installers. Info drainage for Civil 3D installs as a ribbon within Civil 3D and is designed to allow the exchange of data between Civil 3D and info drainage via a parts mapping manager. And that's where we'll be focusing today, working through the demonstration steps. We have two workflow options for using info drainage for Civil 3D. And from working with our customers, the optimal workflow usually starts in Civil 3D, which is where we'll spend more time today on that workflow on the left-hand side here. As the pipes and manholes are often part of the drawing, we lay them out using the pipe networks, then export them to info drainage. Here we can complete the rest of the design aspects, including refining the design, sizing the pipes and manholes, adding in storage structures and green infrastructure devices, and completing a full hydraulic analysis to assess the performance of the system altogether. Then we bring the completed design back into Civil 3D, where the rest of the site design lives. If we choose to start in info drainage, we have the option to start with either storage green infrastructure features and connect them up, or start with a pipe layout and add our storage or green infrastructure features. Either way, there's multiple options to lay out that network. So we can manually lay that out, tracing over background data such as a CAD GIS file or image data. But we can also import some of that data from CAD files, from GIS or text files. Then in the middle part, the steps are the same. We complete the design, size the pipes and manholes, size our storage structures or green infrastructure devices, and assess the performance with hydraulic analysis. And then finally, we bring the completed design back into Civil 3D. But that's not how it works in practice, is it? Iterations always occur, and we need to go around the loop multiple times. So we'll talk more on that later. As we walk through some of the steps needed today, we'll focus on the aspects that relate to using info drainage for Civil 3D, rather than on setting up pipe networks in Civil 3D or the standalone info drainage package. But I'll include some links in the handout so you can find out more details about some of the info drainage workflows. But to start here, we've got a simple pipe network laid out just with one pipe size and one manhole type. Ensuring that the info drainage for Civil 3D ribbon is installed, the next step is to select the option to export to info drainage. Then we're presented with the parts mapping manager, where the Civil 3D parts are detected along with the info drainage object type, for example, a pipe or a circular manhole. We then need to enter the appropriate dimensions. In this example, it's pretty straightforward. With more complex setups where we have already specified multiple pipe sizes and multiple manholes, we could choose to save that to a template that could be used on other projects. Once finished, an info drainage file is saved, which can then be opened in info drainage. And we can see the pipes and manholes have been created, the layouts as it was in Civil 3D. Though catchment areas are not currently supported, they can be quickly imported from a drawing file if we load that as background data by using the option to convert one of the layers to inflows. That generates the catchment areas seen in green here. We could also import that from a separate CAD file or from a GIS file. Then with a pipe network, we would use the network design tools to size the pipes for accepted flow capacity and to meet additional design criteria such as slope requirements, minimum cover level, backdrops, velocities, and outfall requirements. We could then also add storage and green infrastructure and complete the hydraulic analysis to check against performance criteria. With that design complete within info drainage, we go back to Civil 3D, making sure the file's been saved, and use the import from info drainage option. Import from info drainage. Again, we use the parts mapping manager on import. It looks a little different. We can see that we've generated new pipe and manhole sizes having used the sizing tools. And we have to select the Civil 3D part family and part size from the parts list that has been selected. This is automatically stored if we're round tripping, so we don't have to reselect the same size pipe or manhole each time, only new ones that are added. But it can also be saved as a template. So if parts catalogues are the same on multiple projects, for example. The pipe network in Civil 3D is then updated with the design from info drainage, which we can see by interrogating it, and the internal pipe diameters and levels and so on have been updated. This was a simple design. Here we can take a look at the export in a quick video. So we're adding a pipe using the pipe networks option here. And as we run through the export to info drainage from within Civil 3D using the info drainage for Civil 3D ribbon, the parts mapping elements would take place once we've saved that file. Then we open the file in info drainage and we can see that the network has been imported, a slightly more complex version of the design than shown in the individual steps, and we can then go and interrogate that in info drainage and run through those various design aspects. This next video shows a later stage in the design project where we're importing updated pipes as well as more complicated green infrastructure elements, which we refer to as stormwater controls in info drainage. So again, we're using the info drainage for Civil 3D ribbon. We've selected the info drainage import from info drainage option and use the parts mapping manager, in this case, selecting a file that has been saved. Here we get to see the benefits of the accurate layout of those stormwater controls or green infrastructure elements. You can see in the visual representation of the design in the 3D orbit that not only are the stormwater controls themselves laid out accurately, but the location of the inlets and outlets and therefore the correct connection locations have been maintained. We can also make design updates. So if we then get an updated drawing or we want to redesign within Civil 3D, we can move elements, make a change, run through the export process again and open that in info drainage and see those changes have been adopted. This can be repeated as many times as required, either updating in info drainage or updating in Civil 3D, round tripping the data and with those parts mappings saved. And this round tripping of the data gives the engineer greater flexibility in that workflow in terms of exactly which package they make the updates in, and enables those objects to be represented in 3D in a quicker way so that we can comply with the requirements for BIM. Let's discuss some of those complex objects in a bit more detail, because the singular pipes and manholes are fairly straightforward. If we look first at different complex connection representations, singular pipes and box culverts are supported by the native pipe networks in Civil 3D, so the mapping is fairly straightforward. When we come to rectangular, trapezoidal, or triangular channels, as we refer to them in info drainage, these are represented as corridors. So in this example, we have a bypass channel alongside one of our bioretention areas. This is an open channel section within info drainage, but when imported, we don't have that option in the pipe networks in Civil 3D. So it's represented as a corridor. We also have a lagged flow and no delay type connection in info drainage. These are both conceptual connections that can be used to connect objects where we don't know the real physical connection that exists, or where we're perhaps early in the design process and we just want to connect different structures together. Because they're conceptual, they don't have a real physical aspect to them, so they are just imported as polylines. Another aspect that isn't supported at the moment is multiple barrels. So within info drainage, we can have multiple barrels on a pipe, double, triple, and more. These, when they're imported to the Civil 3D pipe networks, are represented as multiple singular pipes, but they're tagged so that they can be supported for the round tripping. And the same goes with intermediate points. So this open channel section, for example, if that was a pipe, it doesn't follow a straight line. There's actually intermediate points, and that would be represented with short sections that have null structures in between them. Again, it's tagged so that it can be supported for round tripping. So moving on to the stormwater controls. These, again, are represented in a lot of detail in info drainage, but don't have an equivalent within the Civil 3D pipe networks. So they're represented with feature lines connected by mesh surfaces. This is so that we can maintain the freeform outline of these structures, in particular for bioretention areas and ponds. They're very rarely rectangular and often not symmetrical. As you can see from the diagram, some of them can be quite complex. So we've broken them into a few different categories: cellular storage, chambers, which could be like these arch chamber storage options, an infiltration trench, which would just be the base part of this dry swale picture, porous paving, and individual soakaway trenches would be represented by top and bottom feature lines. So these are usually have vertical sides, and so there's a top and bottom feature line and then a mesh surface in between, but their shape may not be rectangular. The ponds and tanks can be a little more complex. So you can see on this diagram that these can vary with depth. They're represented in info drainage with a depth, area or volume table, and there's a feature line per entry. So we maintain the shape of those with the mesh joining those feature lines. Then our bioretentions or swales, which this top section here is a swale, but it could be a dry swale with a trench underneath, would have a feature line at the top of the open section, which we refer to as a ponding area, at the base of that ponding area, and then at the base of the storage or the base of the filtration layers. Again, connected with the mesh surface. Now, these feature lines can be edited for round tripping. So we can change the shape of that feature line, and we can actually change the levels as well to make them deeper or shallower. And they're, again, maintained with the round tripping they're tagged. In addition, we have a few other objects that have to be represented by null structures that aren't connected to a particular object within Civil 3D. So if we look at this bioretention area, for example, the inlet and outlet location, so this is likely to be a physical structure. It might be a head wall, and the outlets where we have an orifice and an overflow weir here would appear as a null structure when imported using info drainage for Civil 3D. And the same would go for a simple junction, which is usually used where there's not a physical manhole connecting multiple structures. So looking at some of these complex structures in a bit more detail when they're imported, this example here includes a few no delay connections connecting the manholes to the pond, and also includes multiple green infrastructure elements. We can see that there's a warning on import because there's a cellular storage stormwater control, and it has vertical sides. So we just make a tiny increment to the top area to ensure that that is supported within Civil 3D. Then when it's been imported, we can see the pipes, the manholes, we can see these more complex green infrastructure elements. And using the live links to the help, we can actually go and look at the documentation to understand more about how these different structures are represented. So you can see some of what I've already run through here, but if you need to cross-reference or look it up at any point, it's available from within the software. Going back into Civil 3D in a moment, we'll take a look at the pond in a bit more detail. That object actually includes the connections to it, the inlets and outlets. And we can see how it's represented within a 3D view. So we'll be able to see the feature lines and the actual mesh connection there, and see that the locations are accurate in terms of the inlet and outlet locations, and that structure, it has been brought across from info drainage with the same outline. So if we edited those feature lines, made it deeper, that would be maintained in the link. Looking at that round tripping, just a couple of other tips to cover. It's important to save the info drainage file with the same name. So having exported from Civil 3D to info drainage, we'll have created an info drainage file. That, if we keep that name, it allows the objects to be recognized on the round trip so that we can make sure they're updated. There's also a few objects that, although we have representation for them, if they're moved or deleted in Civil 3D, they'll lose their mapping. So multiple barrels and intermediate points on connections, such as this bypass channel that we saw in 3D previously, would lose their mapping if they're moved or deleted. In the case of multiple barrels, a new single barrel connection would be exported to the info drainage design. And in the case of the intermediate points, singular sections would be exported. Then if we again look at this example here of the bioretention, where we'll have null structures created for the inlets and outlets, if they're moved outside the outline of the stormwater control or deleted, info drainage would need to create a new object on export. And that's to maintain the connectivity of that network, so that the pipe upstream can be connected to that bioretention and so on. So just a few extra tips on the round tripping there. Coming back to our initial learning objectives, I hope you can now use info drainage for Civil 3D to import and export all aspects of your drainage design. And having reviewed some of the more complex objects and round tripping aspects, you'll be able to adopt those design iterations more easily. If we can optimize the drainage design workflows by using info drainage for Civil 3D, then engineers can more efficiently represent their design, reduce data errors and data loss, and more efficiently, with less manual steps, complete the drainage design, giving greater confidence in the validity and accuracy of design information. Thank you very much for joining the session today.